Hello, my name is Karen Levescu, and I will be discussing some of the ways that multimodal data has been used in self-supervised learning for speech, including a mix of both older and newer methods. So we all probably agree that speech is a multimodal phenomenon, but what do we mean when we say that? So there are a number of things that we know from research on human speech, and there are a number of ways in which multiple signal modalities come into play in human speech perception and learning. So first, we know that when we see a speaker's face, we can understand their speech better, effectively improving the signal to noise ratio by about 22 dB. And when we listen to complex speech or accented speech, being able to see the speaker also helps us to understand. We also know from work by McGurk and McDonald in the 70s and follow-up work later on that the human speech perception mechanism automatically combines visual and auditory cues to the point that we can't ignore the visual cues even if we try. And this holds for both adults and infants. And finally, we also know that children learning their first language use visual cues to help learn the phonetics of that language. And it's not, this combination of multiple modalities doesn't have to do only with having access to the speaker's face. It also has to do, for example, with how the visual scene around a listener can inform their understanding of the content. So in the examples in these photos where two people are talking while looking at a scene of some sort, the listener has some idea that the speaker is often referring to something in the visual environment, and this informs how they interpret the speech signal that they're hearing. And besides the visual and auditory modalities, there are also other modalities that affect how we perceive or learn speech, such as the tactile properties of the environment, the smells of the plants in this bottom image, and the internal state of the listener. And all of these observations suggest that machines should also be able to take advantage of all of these cues in learning and perceiving speech. And in the terminology of self-supervision, the additional modalities besides the audio can provide different ways to design proxy tasks for learning a speech representation. So for the rest of this section, we'll sort of distinguish between two kinds of modalities. The first are what I'm referring to as intrinsic modalities, meaning signals that are associated with the speech itself. And this includes the audio signal, of course, but can also include images of the speaker's lips, as well as more exotic modalities like articulatory trajectory measurements, muscle activations, MRI recordings, ultrasonic signals, and so on. And usually the main idea in using these additional intrinsic modalities is that they are highly correlated with the acoustic speech signal, and so they can be used to remove noise or improve robustness to noise or nuisance parameters. And the second type of multimodal speech data is what we're calling contextual. So contextual modalities are additional modalities that provide context besides what is in the speech signal itself. So these kinds of signals tell us something about what the corresponding speech is about, and can therefore be used to learn a more semantic model. And these can include images or videos of a scene that the speech is associated with, or in a robotics setting, it can be associated with a robot's sensory input or information about the robot's state. Most work in multimodal self-supervised learning for speech has focus on visual modalities, and so we'll mostly be thinking about those, but in principle, the methods can apply to many kinds of contextual modalities. Okay, and here's a timeline of some of the methods that you'll be seeing in the next few slides. And this includes both somewhat older approaches from a decade ago through methods that are being presented here at ICASP. And the methods here are divided into learning with intrinsic modalities in blue and then contextual modalities in green. Okay, so we'll start with methods that learn from intrinsic modalities. And this is often referred to as multi-view representation learning or multimodal representation learning. And so the basic setting is that we have training data that are unlabeled, but where each training point consists of a pair of examples, let's say vectors, one from each modality. So in this figure, X is a vector with dimensionality dx, and it might represent speech input, and it might lie on some manifold represented by this S shape. And while Y is another intrinsic modality, for example, the speaker's face, and it might lie on this other manifold shaped like a Swiss roll. And the objective is typically formulated as finding a representation of each view that is in some sense predictive of the other view, or that jointly represents both. And the intuition for that is that if there's noise in the two views, so if we were to add noise to these data sets lying on these manifolds, it might be harder to understand the structure of the data. But if the noise in the two views is independent or at least uncorrelated, then any shared information must be signal rather than noise. And then finally, at test time, we can assume that either one view is available alone or perhaps both views are available together. One approach in this category is multi-view autoencoders, and this is based on a paper from 2011 on multimodal deep learning, where the idea is that the network takes as input one modality, say the video input, and encodes that input into a representation. And then the decoder reconstructs both of the modalities. So the learned representation should include information that is needed to represent both of the modalities. Another variant of this approach, seen on the right here, is to learn an encoder that builds a representation from input in both modalities and again reconstructs both. And which variant is preferred depends on whether we're in a setting where just one or both modalities will be available as inputs. In both cases, the model is trained with a reconstruction loss. A somewhat related model is multimodal deep Boltzmann machines. These are undirected graphical models learned with a maximum likelihood objective, where the nodes at the bottom of this figure represent input vectors in two modalities, and the nodes at the top represent the joint representation. Deep Boltzmann machines were very influential for some time in speech processing as a way to pre-train neural networks, but more recently they have not been in use as much. Another set of techniques is based on the objective of canonical correlation analysis. CCA is a classic linear technique that finds linear projections of each view or each modality that maximizes the correlation between the projected views. And this is constrained by uncorrelatedness constraints in each view. And this objective, this problem can be solved by solving an equivalent eigenproblem. And it also has an interpretation as a constrained reconstruction. It has a number of appealing theoretical properties. For example, under some mild assumptions, it removes noise from the signal if the noise is uncorrelated across the views. And CCA has been used for multimodal representation learning, but more recently it has also been used for a variety of other in a variety of other settings, for example, for analyzing neural networks. And we'll see an example of that in part 2 of this tutorial. Of course, as a linear method, CCA has limited capacity to learn complex representations, so a number of nonlinear extensions have since been developed. One nonlinear extension of CCA is Deep CCA, shown here on the left, where the same canonical correlation objective is maximized, but now the linear projections are replaced by deep neural networks. Another extension is Deep Variational CCA, which is based on a generative interpretation of CCA. More recently, models based on multi-view or multimodal contrastive losses have become more popular. We've seen contrastive losses earlier in this tutorial, where the idea is to learn a representation model such that similar inputs are mapped to similar representations and dissimilar inputs are mapped far apart. In multi-view contrastive learning, we're learning two representation models, one for each modality, so that pairs of representations corresponding to matched pairs of inputs in the two modalities are close, while mismatched examples or distractors are far apart. This idea was used to learn multilingual embeddings back in 2014, and since then, this loss and a number of variants of this loss have become very popular in multimodal training settings. Fast forwarding to this year, a multimodal extension of Hubert has been proposed for learning audio and visual representations jointly from audio-visual speech data that is speech audio paired with the corresponding video of the speaker's face. And like Hubert, which you saw in the previous section, the model is learned with a mass prediction loss and is learned to predict discrete cluster IDs, but now the discrete cluster IDs are learned from the audio and visual signals jointly. I believe that this is the first model to apply recent self-supervised learning ideas to these intrinsic modalities of audio-visual speech, and it seems quite promising in that it produces large improvements in performance in both lip reading and speech recognition. Okay, so far we've looked at methods that learn from intrinsic modalities, and next we'll look at learning from contextual modalities. And this has actually been the more common type of self-supervised multimodal learning in the very recent literature of the last few years. So the goal in learning from speech audio paired with a contextual modality is that the contextual modality informs the model about what the speech is about. So the hope is that it allows the model to learn higher level semantic information. One of the things that has really advanced this research area is the large number of new data sets of images with spoken captions. And this table shows a few examples collected in a recent survey paper by Hrupawa, which gives a really nice overview of this area. And these data sets, which have been collected at MIT and University of Grenoble, among others, now contain up to almost 1,000 hours of speech spoken by hundreds or thousands of speakers, along with their corresponding images for a number of languages. And a related type of data is video data sets that include spoken descriptions or instructions, for example, for cooking or for bike repair and so on. And here again, just like with spoken captions, the speech is assumed to be describing the video in some sense. And in many ways, this is a richer data source because it includes dynamic scenes. But it also introduces new challenges because the spoken description of a scene isn't necessarily well aligned with the corresponding visual content. Okay, so these large data sets have been very important for advancing this research area of learning speech representation models from speech with contextual visual modalities. And the most common approach for learning has been using a pair of encoders, one for the audio and one for the visual modality, that are learned with a contrastive loss of some kind, so that matched image and caption pairs produce similar representations and mismatched ones are dissimilar. And the figure here is one example of this style of model taken from Harwath et al.'s NeurIPS 2016 paper. And the contrastive loss here is very similar to the one a few slides back, but it combines two contrastive loss terms, one each for distractors from each modality. And this work has generated a large number of variants over the last few years, and they've mostly been evaluated in the context of cross-modal retrieval tasks. But they've also been used for other purposes, like to discover spoken terms corresponding to image regions, for example. Most recently, visually grounded speech models have been extended for use as generic pre-trained representations. For example, the model shown here is the FastVGS model and the related FastVGS Plus model, which I believe is the first transformer-based visually grounded model. And it's initialized with Wave2Vec2 parameters and then trained with a combination of a cross-modal retrieval loss and a masked language modeling loss. And this model does not only do well on cross-modal retrieval, but also performs competitively on benchmark speech-only tasks. And we'll be hearing more about these benchmark tasks in the next section of the tutorial. This model does especially well on syntactic and semantic tasks, which is what we might hope to see in a model that is trained with visual grounding. So that brings us to the end of this section on multimodal self-supervised learning. And just for reference, these are all of the papers that have been mentioned in this section.